Okay, we can start. Welcome everyone to this class. Maybe I'll just start with some administrative, just organizational stuff, just for the homeworks. So the way it works, so just so the homeworks, they are handed in class. On the subject of the class, so this is homework 1, it's going to be on this week's subject. And if you do them, and I of course encourage you to do so, please give them back on in the mailbox of the assistant. Your assistant is Min, who is back there. So give back in Min's mailbox, let's say before Friday afternoon, Friday, say 4 p.m., so that he can grade them. And then they're discussed in class, well, discussed in the homework session. The week after. And so, of course, this week there is no homework session, okay? None this week. Okay, and I think I have to inform you about the exams. So the exam is an oral exam in June. You need to have a 4 to get the credits, okay? To get 5 credits. I think that's about it for organization. I don't know if you have questions about all this. Okay, very good. Now, I'm the academic advisor of the department, so now I know what we're supposed to tell the students before we start a class. Okay. Maybe I can give you now a rough plan of the class. So there's going to be 2 parts. Part 1 is going to be about the Dimer model. And I will be a little bit more precise. Here we'll have, so this will last around 10 weeks. So we can say most of the class is going to be, most of the course is going to be about the Dimer model. First part is going to be about perfect matchings. On abstract graphs. Second chapter about dimer configurations on surface graphs. So in the first part, we just look at the graphs as abstract combinatorial objects, and then in the second part, we'll embed them in surfaces, and we'll see that this changes everything, surprisingly. And then in the third part, we're going to look at dimers on, let's say, bipartite, biperiodic graphs. So I will start by asking very general questions that are in full generality impossible to answer, but then we'll see that if we move to surface graphs, we can say quite a bit. If we move to biperiodic graph, we can answer all these questions, basically. It's going to be moving in this direction. And then part 2 will be about the Ising model. Will last around 4 weeks. And it is still too early to give you a more precise plan of part 2. but it's going to build on part 1. Okay. Good. So let me start. So part 1. The Dimer model. And I will start with an introduction. The aim of the introduction will be not only to explain the kind of questions we'll try to answer, but also maybe to settle some notations. Okay. So I'm going to introduce objects that you know very well, but just we were going to set up the notations so that we agree on what we're talking about. Okay, so a graph G is a finite non-empty set Vg equals V of vertices together with a set of unordered pairs of vertices. So this set will be E called edges. And so let me draw one geometric realization of a graph. We will allow multiple edges, and we will allow loops, even though actually, as far as the Dimer model is concerned, basically we can assume that the graph is simple, that there are no multiple edges in loops, but we can work with this, that's fine. So let me just put this as a remark. We allow multiple edges in loops, although we can assume that there are none. i.e. that the graph is simple. That's the definition of a simple graph. Okay. Okay, that's one thing to define. Next, what is a bipartite graph? So if there is a partition of the vertices of the graph into two subsets, such that each edge of G joins an element, a vertex in B and a vertex in W, then G is called bipartite. Okay, so B and W stands for black and white, which of course is a great mistake to do when you write on the blackboard, right? Because now I will never know what is white on my sheet of paper is going to be black on the board. But anyway, let's take, for example, a part of a square lattice. That's a bipartite graph. We have a bipartition into black and white. Okay. Okay, next object I want to define, a matching in a graph G is a set M of edges whose elements are vertex disjoint. Okay, they don't intersect. A matching is called maximal if it is maximal, that is, if its size is greater or equal to any other. And finally, a matching is called perfect. Perfect matching if it matches all the vertices of the graph. This means a perfect matching is a choice of a family of edges such that each vertex is adjacent to exactly one of these edges. Okay? Here is a perfect matching on this graph. That's a perfect matching. And we will write some kind of calligraphic M of G for the set of perfect matchings on a graph. Okay. So that's about it for the notations, terminology. And now let me ask some questions. So first question. First question to ask, does a given graph admit a perfect matching? And if yes, can we find one? So now I'm not being very precise. So of course one can always answer these questions, right? We have finite graphs, so okay, you just try everything and it works or it doesn't work. But here the point is I want to do this, and will not be precise, we'll be more precise later, in an efficient way. Okay? For example, it means something like in a polynomial time, if we have a polynomial time algorithm to find a perfect matching or a maximal matching, you know, this kind of problems. Okay. That's the first question we're going to address, and maybe yeah, I don't want to give the punchline already, but okay. Anyway, this one, it turns out, is an easy one. It's not difficult to answer this question in full generality for an abstract graph. But maybe I'll just give some motivations. Here, the motivations come from real life problem, as one says. for example, you have students that sign up in a university. There are bedrooms for 2. They say who they would agree to be with. And what do we get? So you get a graph. So the vertices are the students. You have an edge between 2 students if both agree to be together. And okay, then finding a maximal matching means the biggest number of students are happy, basically. Perfect matching, all the students are happy. Okay. So this gives a graph. And finding, so maximal matching is the same as making the most students happy. Well, the biggest number of students happy. Then you can do the same thing with men and women, for example, right? So if you have a website, matrimonial website, etc. So the men and women say, okay, I would like to be with this guy. I would like, same thing. It's exactly the same problem, but on a bipartite graph, right? Assuming that they're all heterosexual, that's what happened, okay? So same with men and women. This gives a matching on a bipartite graph. And this gives rise to what is called the marriage theorem. We're going to see this. Okay. So as I said, this one actually is not a difficult one. Maybe you already know about this. I see some of you nodding. But this is not a difficult one. We'll see how to answer the question, and it works really on any abstract graph. Now here's the second question. Building up, let's say, on the first one. Can you actually count the number of perfect matchings on a graph? Can we count the number of perfect matchings on a given graph? Again, obviously, you can always do it if you have a lot of time, and okay, but we want to do this in an efficient way. So I don't know if you know about this, but this one is much more tricky. So again, I don't want to give away too much, but this one actually, the answer is no, you cannot do it in full generality. If you have just an abstract graph, you cannot. There is no algorithm. Well, on the other hand, it turns out that if you embed your graph in a surface, then you can do it. It's quite amazing. So if the graph can be embedded, well, let's say if you have a planar graph, then you can do it. That's going to be a big part of chapter 1.2, trying to explain this. Maybe I'll give some motivations. So here the motivations are not so much into a real-life problem, but more combinatorics, natural questions in combinatorics. So natural questions in combinatorics. For example, here is one question. So let's say that you have a board let's say that in my case a 4x4 board, but in general an m times n board. So, and you want to tile this board with dominoes that are 2x1. Okay. Question, how many tilings, how many domino tilings do you have of an n times m board? So how many domino tilings of an n times m board is there? Okay, so here I'll just give you one tiling here. I don't know if you can see it well, but anyway. Yeah, to me it's not very visible, I don't know for you. So anyway, the point is that you understand that this is the same as giving a perfect matching on a square lattice, right? So I'm just gonna use another color. You see, if you set a vertex inside each face, what you will get is an n times m square lattice and a domino tiling. So you just put a matching, an edge of the matching whenever you have a domino. For example, here, so maybe now I should use the blue. You put an edge here along each domino, and what you get is exactly a perfect matching on the graph. Okay, so this is the same number of, so I'll just write like this. The cardinal of the set of matchings, perfect matchings on an n times m square lattice. And amazingly, we'll see a closed formula for this. So a formula that gives you exactly the number of matching. This is really quite amazing. That was solved in 61 by Castellane. We're going to see this. And maybe I'm just going to also write here, how does this number grow? This is, of course, not precise at all. This number grow if G gets bigger. Not precise at all, but of course, here you can imagine it. You can see, you can say, okay, you have let's say an n times n square lattice or board, and you take n to be big, and how does it grow? So it's the number of perfect matchings is exponential. It's something like exponential of n squared times a constant, and we'll compute this constant, the growth of this number. Okay, but this is of course just one example, but you can do the same for example, how many lozenge tilings of some given shape, of some given domain is there. I'll try to make a drawing, so maybe I will do it here. So let me draw for you a lozenge tiling. Okay. So this is a lozenge tiling of this shape that I started with. And do you see So you see what it corresponds to in terms of perfect matchings, right? So it corresponds to a perfect matching on an underlying hexagonal graph, right? So here what we're really doing is we're taking, let's say, dominoes. Here, of course, the basic, so the face were squared. Here the faces, they are triangular. And what we're doing is that we're looking at the dual graph, the dual of this triangular graph, that is hexagonal graph. And this is equivalent to having a perfect matching on the underlying hexagonal graph, right? Of some hexagonal graph. But the reason why I took some time to make this example is that actually, if you look at it, you can also see it as some kind of stepped surface, you see? As some kind of discrete surface. And this is important. It's nice to know that, as we'll see, the Dimer model can be interpreted also as some kind of model for step surfaces. So this, let's say, a discrete surface. Okay. Okay, so far we're really only doing combinatorics, but really we can now pimp up this setting into a full-blown model of statistical physics by putting weights. So now consider consider an edge weight system I will denote it by nu. So means to each edge of the graph we assign a positive weight. Still a finite graph. So this and those, the set of perfect matchings on the graph with a probability measure. Mu, which depends on the weighted graph, as follows. So mu of some matching m will be equal to 1 over z mu of m, where mu of m is the product of the weights of all the edges in perfect matching, and of course z is the sum over all perfect matchings of the corresponding weight. Z, as you know, is called the partition function of the Dimer model on the weighted graph G nu. So the Dimer model is really the study of this measure here.
Why do I want to define this measure knowing the question was just to count the number of perfect matchings?
Why do I want to define this measure?
Yep.
Well,
just that our question is purely combinatoric at the beginning, so.
No, sure. So, okay. So there are many ways to answer your question. So first way is, actually, I will be able to tell many things about this model. And if you just set all the weights equal to 1, you will have answers to all the questions you want in combinatorics. And most of the time when you're able to answer things with all the weights equal 1, actually you're able also to answer the same things with the weights here. Okay? That's one way to answer. The other, I mean, basically you will see along this first part of the class that, well, it's very interesting to actually tweak these weights, and that we will see that the model exhibits different behavior when you change these weights, and therefore, okay, it's useful. Then the last way to answer your question is actually, for example, if you want to study the Ising model, it turns out that to study the Ising model, you can map it to something in the Dimer model where you have some weights that come, and if you're able to say things about the Dimer model, then you can translate this into the Ising model, etc., etc. Okay. But I think the answer will be, you will, basically the whole first part of the class it will be an answer to your question. Okay, so now I can generalize question B that I'm just erasing now into question C. So let's extend question B to question C. Given a finite weighted graph, can we compute the corresponding Dimer partition function? Again, in an efficient way, okay. And you understand, of course, that this generalizes question B, because if you set mu equal 1, then Z is simply indeed the number of perfect matchings. And maybe, so I had a second part in question B, which was something like, how does it grow? How does this number grow? So the corresponding question for the Dimer model is, again, it's not going to be precise, but given a sequence Gn growing to some infinite weighted graph G, can we compute what is called the free energy? The free energy of the, which is something like you see, if you set all the weights equal 1, what you're really computing is the growth rate, to speak of the number of perfect matching on your graph. In general, it's called the free energy of the model. Again, I'm not being precise at all here, of course, but okay, you can imagine. Motivations. First motivation, in some special cases, it gives us statistical models for random tilings or step surfaces and things like this. So in special cases, models of random discrete surfaces tilings, etc. Another motivation that I read many times, but I don't know so much about it, it's actually supposed to model the absorption of diatomic molecules by a surface of a crystal. So the word dimer comes from this, so that like polymer, so that dimer means one bond, two atoms. So I'll just write this down, but I really cannot explain to which extent this is actually meaningful, but let me write it. The Dimer model models the absorption of diatomic molecules, hence the name, and that's really the only reason why I give this, dimers, by the surface of a crystal. Third motivation, you can use it for the Ising model. That's what we're going to see in the second part. To study the Ising model. And several other models. I mean, actually, I heard many times the kind of vague claim that any exactly solvable model in statistical physics can be mapped to the Dimer model in one way or the other. I will not try to give a proof of this claim in any way, but okay. For example, the Ising model can be mapped into the Dimer model, and it's because we're able to solve the Dimer model that then we can pull this back to the Ising model. But now I'm going to give you the real motivation. I mean, the real reason why everybody is studying the Dimer model and not another model. Can somebody guess? It is at the exact right level of difficulty. So you have these questions that are really difficult. Most of the time you cannot answer them, but sometimes you can actually answer them very beautifully. And you have amazing results. You change a little bit the model, you cannot say anything. That's a good enough reason to study it, right? So it is you have another model called the Dimer Monomer model, where you allow to have vertices, well, it corresponds to having matchings that are not perfect. You're allowed to have vertices not matched. Try to compute the partition function, even on a square lattice, it's impossible, where it's very difficult, you see? So, but it turns out, for some kind of miracle, for the Dimer model, you can you can solve it very beautifully. And this is basically the aim of the class, to explain this. Okay, I think I'm done with the introduction. Yep. Any questions about this? Okay. So I'll start the class itself. The first, so I'm going to put titles maybe in yellow like Hugo. The first part, as I said already, perfect matchings on abstract graphs. So in this part, we try to answer these questions for just abstract general graphs, okay? We try to answer these questions for general graphs. General abstract graphs, that's the point. Meaning not embedded. And as we will see, question A is fine, and question B, it already collapses, more or less. And we have to stop there. So first question was, does a graph admit a perfect matching? Okay, so this part will be basically I will prove a theorem which is called Tute's theorem, which gives you a necessary and sufficient condition for a graph to admit a perfect matching. So in this part, in this section, we prove Tutte's theorem and give consequences. So there is one standard reference for matching theory, a book which is actually called Matching Theory, and it's by Lovatz and Plummer, and they call Tutte's theorem the most important result in matching theory. So let's explain this. Maybe, okay, I'll just go to the statement and then we'll make a break. So I just need a notation. For a graph G, let CO of G denote the number of components of G with an odd number of vertices. Okay? So the first remark to make is that if G admits a perfect matching, then C0 of G is 0. Sorry, it's CO. That's the little O here is, the circle here is for O, like odd. C like components, so number of odd components of G is equal to 0. You all agree with this, right? You have a perfect matching, you just match them in the components by pairs. You cannot have odd components. So the first question is this sufficient? So does this mean that then you have perfect matching? That's not the case, so this is not sufficient. For example, just consider the graph G like this. So okay, you have 4 vertices, no odd components, but you don't have a perfect matching here. Okay. So we have to refine a little bit this condition. So actually, if G admits a perfect matching, then C0 of G minus, well, then for any set of vertices, the number of odd components of G minus S is less or equal to the number of elements in S. So here, G minus S, right, I removed the vertices and all the adjacent edges. This holds. So I'm going to tell you why in a second, but just note that this condition is a refinement of the previous one, because the previous one corresponds to S equals empty set. Okay? S equal empty set gives C0 of G equals 0. CO of G. So do you understand why this is true? So you remove this set of vertices with adjacent edges, and you have these matchings. You see, what happens is that each odd component here must send out an edge, an edge of the matching to S, right? Because if you have an odd number of vertices here, but they're matched by M, means that at least one of them must be sent outside by M, right? So, indeed, if G has a perfect matching M, then each odd component of G minus S must send at least one edge of M to S. Right? Okay. Have an odd number, so okay, one of them must be matched outside. We matched to S. But then each element of S receives at most one of them, because it's a matching. You cannot have two edges of M going to the same element in S. But each element of S receives at most one such edge. So we have an inclusion. This defines an inclusion from the odd components of G minus S onto S, into S. Right? So it means the number of elements here is smaller or equal to the number of elements there. Do we have a chance for this condition now to be sufficient? Well, here, indeed, we have a problem, right? If we take S to be this vertex here in the middle, then the number of odd components of G minus S is 3, which is greater than 1. So, indeed, so here, I'll just write here, S equals V gives C0 S equal 3, which is strictly greater than 1. And indeed, Tute's theorem is the statement that this condition is actually sufficient. So theorem Tute around 47, that's right. So a graph G admits a perfect matching if and only if CO G minus S is smaller or equal kernel of S for all maybe just before making the break, why is this an interesting result? Of course, we'll understand later also why it's interesting. But, well, for example, it allows you to, okay, first, it actually implies a lot of classical results in matching theory. And maybe I will speak a little bit later about why this is a nice result. I mean, if it's not obvious to you that it's a nice statement. I suggest we make a 15 minutes break. We start at 20 past. I will give the proof of the theorem and probably one consequence and then stop there. Okay. Okay. We resume. So let's give the proof of this theorem. So the proof that I'm going to give is due to Lovatz. How to spell his name? Lovatz. 1973. I think it's a very beautiful proof. Okay, so one side we proved already. This side, it's fine. And now we have to prove the other side. Okay. First, note that we can assume that G is simple. Okay, you just think for a minute, the loops, they don't play any role. If you have multiple edges, you just replace them by one edge. It doesn't change anything in either side of the statement. Okay, so remove loops. Replace multiple edges by one. Okay, so what we're going to do is assume that G does not admit a perfect matching, and then we'll try to find S such that. Okay. So let's assume that G does not admit any perfect matching. And let us look for S such that, so C0 of G but S is strictly greater than S. Okay. Now, of course, we can assume that G has an even number of vertices, because if it had an odd number of vertices, S equals the empty set would already give us the answer, right? So if the number of vertices of G is odd, then S equals the empty set works, and we are done, right? In this case, we would have at least one odd component greater than 0, so we're done. So we can assume that the number of vertices, I will not write the G, is even. Now here is a really beautiful trick, and I love that. So what we can do is actually add edges until G is edge maximal. So what do we mean by this? So adding edges to G, we can assume that G is edge maximal, i.e., so we keep it simple. Let's keep it simple. So we keep G simple. We keep it without any perfect matching, but it is such that whenever I add one more edge, then it admits a perfect matching. So G is simple, does not have a perfect matching, but G plus E has one for any E that is not in the set of edges of the graph. Okay? Why is this? Indeed, remember, what we're looking for is an S such that this inequality holds, right? So if we have an S in the vertices of G, G edge maximal, such that C0 of G minus S is strictly greater than S, then this same S will work also for any, so then this same S will work for any spanning subgraph G prime in G as C0 of G prime minus S is greater or equal to C0 of G minus S. So do we understand this? So here, to go from G prime to G, I have just added edges. What do you do when you add edges? Well, what might happen is that you might paste together odd components. So you'll have the number of odd components here in the new graph with more edges that will be less or equal to the number of odd components in G prime. Right? So this argument, I hope you agree, allows us to say, okay, we can assume that G is edge maximal. So it does not admit any perfect matching, but whenever you add an edge, you have a perfect matching. Okay? Good. Now here's the claim. Before the claim. So let's summarize. So we have G that is what? Simple. The number of vertices is even. It does not admit any perfect matching, so let's write this way. And G plus E, well, and edge maximal. Okay, and we are looking for an S such that this inequality here holds. And now what is really nice is that you can actually explicitly give the S. So set S to be all the vertices with degree b minus 1. That means it's all the vertices that are linked to all the others. Okay, you just choose all the vertices that are linked to all the others. The set of vertices in G linked to all the others. Okay, and now here's the claim. The claim is that if you take G with this property here and you remove S defined like this, then G minus S consists of complete graphs. I'll just keep this here. Before proving the claim, I will explain why it implies the theorem. Right? So this implies the theorem. Why? So, indeed, if we had CO of G minus S smaller or equal to S, then we would be able to construct a perfect matching on G as follows. And this would be a contradiction, right? So what I'm going to do is just I'll just start with the drawing. So we have the claim which tells us this consists of complete graphs. So we have some odd complete graphs. Okay. These are odd components. Then we have S. And we have some even complete graphs. And remember, S is linked to everyone. So how can we find a perfect matching? So how do we do? So I'll just first make a drawing and then write a couple of lines. Well, this is quite obvious, right? So here, what do we do? First, on the even components, we just match them in any way, okay? So we just match, say like this. So first, match the vertices in the even components. Okay, as you want, as you wish. Then what do we do? In the odd components, we match all of them but one. Okay, so no. Match all the vertices but one in each odd component. But now, since the number of odd components is less or equal to S, and S is linked to everyone, we can link the remaining points to people in S, right? We have enough of them, okay? So since C0 of G minus S is less or equal to S, we can match the remaining elements, vertices in the odd components to elements of S. To S. Remember, S is linked to everyone, so we don't have any problem here. So let me just do like that. And finally, we might have some vertices left here, but we know that S is linked to everyone, so they're all linked together, and the number of vertices is even, so we can then match the remaining ones together, and we're done. Okay? So since V is even and S linked to all, we can match the remaining vertices of S together. Okay? So you agree that the claim implies the theorem. So now this is what we need to check. Everything boils down to this thing here. If we have G that is simple, even number of vertices, no perfect matching but edge maximal, then if we take S like this, then G minus S consists of complete graphs. Okay. So let's try to prove this. And maybe I will keep this here on the board just to remember what we're trying to prove. Can I erase this? Okay. So we are left with the proof of the claim. Okay. So what we're going to do is assume, by way of contradiction, assume by way of contradiction that one component, k of G minus S, is not a complete graph. And then the way we're going to have a contradiction is actually then we're going to find a perfect matching. We'll find a perfect matching on G and be done. Okay. So, saying that one component is not a complete graph, what does it mean? So it means we have, let's say, A, which is adjacent to B, B, which is adjacent to C, but A not adjacent to C. So we have something like that in the component. So A, B, C. So in K. We'll just write like dashed like this, just to say that there is no edge between these two. Okay. Now, B belongs to K. K, so this means that B does not belong to S, and by definition of S, this means that there is at least one vertex that B is not adjacent to, right? S is the set of vertices adjacent to everyone, so there exists D such that B is not adjacent to D. And I'm just going to write it again like this. So have D here. I'm going to put dashed like this, saying, okay, these two, there is no edge here. Okay, now we're going to play a game which is saying, well, this edge does not belong to set of edges of G. G is edge maximal, meaning if I add this edge, then I have a perfect matching. Okay? So since, so here let me just write AC does not belong to E, and BD does not belong to E. So since AC does not belong to E, and G is edge maximal, G plus AC has a perfect matching, let's say M1. And same thing for BD. Since BD does not belong to E, G plus BD has a perfect matching, let's say M2. Okay, now we're going to make maybe I'm just going to make a little aside here, because this is a trick that we're going to use so many times. I want just to make a little parenthesis here. If you have two perfect matchings on a graph, there is one thing that is very sensible to do, is to consider their symmetric difference. So if you have M1, M2, which are two perfect matchings on a graph, here, careful, here of course this is in the graph G plus AC, This is in the graph G plus BD. But so let's say if you have M prime, two perfect matches on a graph, then their symmetric difference, meaning the union of both minus the intersection, you see what this is. So let me just make a little example. So really on a stupid example, let's say that this is M, and I'm going to draw M prime. You see, if you look at the symmetric difference, what you get is a cycle here. An alternating cycle where you have edges of M and N prime alternating along the cycle. It's a cycle of even length, right? So here, this is the symmetric difference. And in general, if you have two perfect matchings, you look at the symmetric difference, what you get is a disjoint union of cycles of even length. Okay? Consists of a disjoint union of cycles, and I'm going to call them alternating cycles. You see alternating because when you go along the cycle, you have M prime, etc. And in particular, they're of even length. Okay, that was just an aside that might have been better to do before, but it's okay. So now we have these two matchings. Let's go back to the proof. So what we do now is consider their symmetric difference, M1 symmetric difference M2, which is now in the graph G plus AC plus BD. Okay, so it consists of, as we said, alternating cycles, okay, CI. So let's say that M1, let us say that AC belongs to C1 and that BD belongs to C2. So, oops. So if C1 is different from C2, if they don't belong to the same cycle, then what do we consider? Then we consider M3, which will be given by M1 symmetric difference with the edges of C1. So okay, I will continue here. Okay. So what do we have here? So we look at M1, and M1 has AC. Okay, and then I don't know, it links the other one like that. Okay. And then if we assume that C1 is different from C2, then what do we have here? So this would be M1. And then you have M2, the elements of M2 like this. And together they form, this part here forms some cycle C1. And now we're assuming that this edge here, BD, does not belong to C1. right? Belong to C2, which is a different cycle. So if this was the case, then if you look at M3, that is, you take M1, what is the trouble with M1? What prevents M1 from being a perfect matching on G? The trouble is that it contains this edge here, which is not on G. But now if you take M1 and you make the symmetric difference along the edges of C1, it means you just take this here and you exchange the yellow and the purple ones along C1. Then what do you get? You get a perfect matching that does not use AC anymore. It does not use BD either because C1 is different from C2, so you get a perfect matching on G. And this is the contradiction. So is a perfect matching on G a contradiction? Again, I hope you got it. So why is it a perfect matching on G? Because since it does not use AC anymore, and not BD either, since C1 is different from C2. Okay. And we're almost done. Hence, we can assume that C1 is equal to C2. And let me make the relevant drawing. So again, we have A, B, C, and what happens is we can start at B, BD here. So this is M2. Then we'll have a path, an alternating path, like this, which, so let us start at BD, which is in M2, and follow the alternating path. Which will at some point arrive here, because C1 is equal to C2, so at some point it contains this edge here. So at some point it will touch either A or C first. Let's say without loss of generality it touches C. So, which will arrive at A or C at some point. Without loss of generality, let's say that it arrives at C. So it continues like this, and then at some point it arrives here. So we have this path here, let's call it P. Okay, now do you see the trick? So then if you look at P and you add the edge BC, this is an alternating cycle, and what you can do is you can take M2 and you make the symmetric difference with the edges of this cycle, and with this trick you will again do the same thing. You will exchange the yellow and the purple ones along this cycle, so you will not be using BD any longer. And since you're not using this one either, it means you have found a perfect matching. So let me write this down. It's the same trick as before. Then, if you look at M2, so let's say M4, which would be M2, symmetric difference with the edges of P plus BC, which again only means you look at M2 and you exchange yellow and purple along this cycle here. Well, if you have here, you're not using BD anymore, you're not using AC, so you have a perfect matching on your original graph. Is a perfect matching on G, and we are done. I think this proof is very nice, and I also chose to present it because it really introduces in a natural way this trick here, which is a very fundamental trick when studying perfect matchings. Okay. Okay, I have 10 minutes left. We'll see. Okay. I'm not sure I want to embark into the next proof, but let's just say. So it turns out that Tutte's theorem implies most of the classical results in matching theory. So we will see now a couple of these results. We're going to have a couple more in exercises. And we'll see a couple of them in class. Some more in homework number 1. Okay. So to introduce one of these consequences, I just need one terminology, a couple actually. So a graph is called cubic if every vertex has degree 3. And a bridge in a connected graph G is an edge E such that G without E is not connected, is disconnected. Okay. And I will state this consequence. It's one of the oldest results in matching theory. Here is one of the oldest results in theory. And you will see probably next time that it actually follows quite easily from this theorem. So it's the theorem of Petersen. Dates back from 1891. Every connected cubic graph with at most 2 bridges admits a perfect matching. So the original statement was every connected cubic graph with no bridges admits a perfect matching. Actually, it can be refined to this. I think that's a quite nice result, and I think it also it's a nice motivation to the theorem that one can then say, okay, such a big class of graph always admits a perfect matching. And I'm not going to prove it now because I would really go over time badly, but I'm just going to make a couple of remarks. So the first remark is can we find an example of a cubic graph that has, let's say, 3 bridges that does not admit any perfect matching. So that, yes, this is possible. So the following example, so the assumption at most 2 bridges is necessary, as shown by the following example. So here is the example. It's kind of a variation on the very easy first one I had. I'm missing something, but we'll come to it. There you go. Like that. I think that's right. So it's cubic, yes. It has 3 bridges, right? And why does it not admit any perfect matching? You see why? So that's the easy side of tutor that says if you take S, so let's write V for this, and if you take S with V, then you see that C0 of G minus S, right? You remove this vertex, you find yourself with these 3 squares here. Each of them has 5 vertices, so you have 0 which is equal to 3, which is greater than 1. So no perfect matching. By the easy side of Tutor's theorem. Okay, and second remark is simply see homework 1, exercise 3 for a nice application of this theorem, Petersen theorem. Okay. So I will stop here. So next time I'll give a proof of this theorem. It's not too bad with tutor. And then I will go to bipartite graphs and explain how Tutor's theorem implies classical theorems which is called Frobenius theorem for bipartite graphs. And then we'll move on to the next question. Can you find a perfect matching in general? We will answer this question. Then we'll move on the week after to the next question. Can you count perfect matchings? And then here we're going to see that we run into problems. Therefore, we're going to move in the next chapter to graphs embedded in surfaces, where here you can move forward. Do you have a question about today's class? Okay. Have a nice week. See you next week.